Okay, so a system of linear equations in three variables contains the lines L1 and L2. Determine if a solution exists for the simultaneous equations. If so, calculate the point of intersection. Describe the geometric nature of the system by referring to any possible solutions. Okay, so our steps for this, currently we've got it in Cartesian form. I'm sure there is a way to solve it in this current form using Cartesian form, but I do think the easiest way of getting around this is to convert it back into parametric form, solve for your values of k, see if they are the same. If they are the same, then that means that given our parametric form, we can substitute k into the equations to figure out what our unique solution is. If k is not common across all three solutions, then that would indicate to us that there is no unique solution for this. They don't intersect at one point. Okay, so let's get started. Okay, so first ones that we're going to convert are L1. So you can see over here that they're all equal to k. So I could have k1 is equal to x plus 6 over 2. First one I'm going to move across is the 2. So I'll get 2k is equal to x plus 6. Then I'll move the 6 across to be left with 2k minus 6. Now I'm not going to go through the working for all of them. I'm just going to jump straight to the solutions for the rest of them. Follow that same process though, if that's what you need to do. Okay, so these are our three equations that we can use to describe the path of L1. Now for L2, we're going to do the same thing again. It's going to be equal to k plus 3 over 4. Now, like before, I'm not going to show you all the working. I'm going to jump straight to the answers. So for the first one, x is going to be equal to 4k minus 3. Y is going to be equal to 10k minus 6. And z is going to be equal to minus 6k, and that's it. All right, so now we've set up our equations. We can start to look at rearranging to find out our values of k, because if I can get the same value of k in all of these equations, that means there is a point that is common. So to do that, we're going to test x1 is equal to x2. Now, if you look in the textbook, they've solved this in a different way. Both ways will get you the right answer. It just depends on how you want to roll with this. Okay, so 2k minus 6 is equal to 4k minus 3. Next one, I'll move this across over here, making it a positive 6, so we'll be left with 3, and I'll take this over there, meaning that I'll be left with negative 2. So negative 2k on this side. Now I've got k is equal to 3 over negative 2. Now, when I do the same thing for y, if I get this solution, then I'm going to test it again for z to make sure that they are the same. If they're the same, there's a unique solution. Otherwise, the other ones that I can look for are whether they're going to be parallel, meaning that they'll have no solutions, or whether or not they're pretty much the same thing, which means that they'll have an infinite number of solutions. That would be that their gradients and their intercepts would all be the same. Okay, so now for your y's. Where's my functions? 5k minus 2 is equal to 10k minus 6. Take this to the other side, I'm left with minus 5k. Take this over here, I'm left with minus 4. That will give me that k is equal to 4 over 5. So they are not the same, therefore there is no unique, Q goes that way, solution. Meaning that it cannot look like this. There is no point where they touch like that given these three systems. So the other thing that we can look for is I can see straight away that, nope, I've forgotten what I was going to say. Oh, well, there you go. We proved that there's no unique solution.